So, how exactly does an engine perform this incredible feat? The core challenge is converting the static, potential energy stored in fuel into useful, dynamic motion. This single question is the foundation of internal combustion. Before we meet the mechanical players, let's understand this fundamental energy transformation.
Our journey begins with the engine's foundation, the engine block. This is a solid piece of metal, typically cast from aluminum or iron, that provides the rigid framework for the entire engine. It's the main stage where all the action will take place, housing the precisely machined chambers that are central to combustion.
Now, let's zoom in on the heart of the engine block, the cylinder. Think of it as a perfectly round, polished arena. It is within this confined space that the entire four-stroke cycle will unfold. Its size, or volume, is a key factor in determining an engine's power and displacement. All the energy of combustion is contained and directed by these strong cylinder walls. Inside this arena, we find our main actor, the piston. This is a cylindrical plug that fits perfectly within the cylinder. Its sole purpose is to move up and down. This linear motion is the very first step in converting the chemical energy of fuel into mechanical work. To contain the immense pressure of combustion, it is sealed against the cylinder wall by piston rings. But the piston's simple up and down motion isn't useful on its own. We need a way to translate it into something that can turn wheels. This is where the connecting rod comes in. It acts as a mechanical wrist, linking the piston to our next component. Its job is to transfer the immense force from the piston's downward push. The connecting rod delivers the piston's force to one of the most ingenious parts of the engine, the crankshaft. This is a specially shaped rotating shaft with offset sections called crankpins. As the connecting rod pushes down, it forces the crankshaft to rotate, much like your leg pushes on a bicycle pedal. This is the critical step where linear motion is transformed into rotational motion. Let's put those three parts together to see this transformation in action. The piston moves up and down. The connecting rod transfers that linear force. The crankshaft receives that force and, due to its offset design, is forced to rotate. This assembly is the mechanical heart of the engine, relentlessly converting the straight-line pushes from combustion into the spinning force that ultimately drives the car. Now that we have our core mechanical assembly, we need a way to control the combustion process. This happens in the cylinder head, which bolts to the top of the engine block and seals the cylinder. It's a complex component that acts as the engine's control center, housing the valves for breathing and the spark plug for ignition. For an engine to run, it needs to breathe in an air-fuel mixture and exhale exhaust gases. This is controlled by the valves. Typically, there are at least two per cylinder: an intake valve to let the mixture in and an exhaust valve to let the burnt gases out. These are precision-engineered poppet valves that open and close at exactly the right moments, acting as the gatekeepers to the combustion chamber. But what tells the valves when to open and close? Their timing is orchestrated by the camshaft. This is a rotating shaft with egg-shaped lobes, or cams. As the camshaft spins, these lobes push down on the valves, opening them. The precise shape and timing of these lobes are critical to the engine's performance, ensuring it breathes with maximum efficiency. So, how is the camshaft's rotation synchronized with the piston's movement? The answer lies in a direct connection to the crankshaft. The camshaft is driven by the crankshaft via a timing belt or chain. This connection forces the camshaft to rotate at exactly half the speed of the crankshaft. This 2-to-1 ratio is fundamental to the four-stroke engine, ensuring that the valves open and close once for every 2 revolutions of the crankshaft, perfectly aligning with the four-stroke cycle we're about to explore. We have the mechanics and the controls for breathing, but we're missing one final, crucial piece: the catalyst for the explosion. This is the spark plug. Positioned at the top of the combustion chamber, it receives a high-voltage electrical signal at the perfect moment, creating a tiny but intense spark that ignites the air-fuel mixture. This spark is the trigger that unleashes all the stored energy. With all our key players assembled, the piston, crankshaft, valves, camshaft, and spark plug, we're ready to see the performance. This performance is a continuous four-act play known as the four-stroke cycle. The four strokes, or piston movements, are intake, compression, power, and exhaust. This sequence is the recipe for converting fuel into force. The cycle begins with the intake stroke. The piston starts at the top of the cylinder and moves downward. As it moves, the intake valve opens, creating a vacuum that sucks a precisely measured mixture of air and fuel into the cylinder. By the time the piston reaches the bottom, the cylinder is filled with combustible mixture, and the intake valve closes. Next is the compression stroke. With both valves now sealed shut, the piston reverses direction and moves upward. This action dramatically squeezes the air-fuel mixture into the small space at the top of the cylinder, called the combustion chamber. This compression raises the mixture's pressure and temperature, making it far more volatile and ready for ignition. Now for the main event, the power stroke. At the precise moment of maximum compression, the spark plug fires. This ignites the highly volatile mixture, causing a rapid, controlled explosion. The expanding gases from this combustion create immense pressure, forcing the piston violently downward. This is the only stroke that produces power, driving the crankshaft with tremendous force. Finally, the cylinder must be cleared to begin the cycle again. This is the exhaust stroke. The piston moves upward for a second time. As it does, the exhaust valve opens. The rising piston acts like a plunger, pushing the spent, burnt gases out of the cylinder and into the exhaust system. Once the piston reaches the top and the cylinder is clear, the exhaust valve closes, and the entire four-stroke cycle is ready to repeat. This raises an important question. If only one of the four strokes actually produces power, what keeps the crankshaft turning through the other three non-productive strokes: intake, compression, and exhaust? A single power stroke would create a jerky, unusable rotation. The engine has a clever solution for this. The solution is inertia. The heavy, rotating crankshaft and an attached weight called a flywheel act like a mechanical battery. They store the rotational energy from the forceful power stroke. This stored momentum, or inertia, is then used to carry the entire assembly through the next three strokes, ensuring a smooth and continuous cycle until the next power stroke provides another push. While a flywheel helps, a single-cylinder engine is still inherently unbalanced and produces a pulsating power delivery. To achieve the smooth, consistent power we expect from a car, engineers use multiple cylinders. By arranging several cylinders to work together, their power strokes can be staggered to create a more continuous and overlapping delivery of force. This carefully timed sequence is called the engine's firing order. In a typical four-cylinder engine, no two pistons are in the same stroke at the same time. While one cylinder is on its power stroke, delivering energy, the others are busy with intake, compression, or exhaust. This creates a symphony of motion where the individual pulses of power blend together into a smooth, constant stream of rotational force. So, let's recap the entire energy transformation we've just built. We begin with potential chemical energy stored in fuel molecules. Combustion rapidly converts this into intense thermal energy, heat and pressure. This thermal energy creates the force that is converted into linear mechanical energy by the piston. Finally, the crankshaft converts that linear motion into the rotational mechanical energy that powers our world. From a simple lawnmower to a complex race car, this four-stroke cycle is the brilliant principle at work. It is a perfectly synchronized dance between dozens of moving parts, all timed to fractions of a second to harness the power of combustion. Understanding this cycle reveals not just how a car works, but the incredible ingenuity that drives our modern, mobile lives.